this is one yet another boondoggle. I will say, so at 5 minutes until 2, I will stop, and those who want to go to this talk can go, and those who don't even want to go to the talk but want to go do something else can just leave, and those who want to suffer the rest can stay. Now, since I don't know most of you, that's proof by example that I'm not in the same labor union. Okay, so I'm a visitor in the astrophysical labor union. We heard this morning the characterization of someone being reasonably truthful. And so I think reasonably honest. We were talking about Galerkin method. So asymptotically, I think the leading order, reasonably honest and reasonably dishonest, are exactly the same.
Relatively honest.
Okay. So I'm reasonably ignorant, and I'll describe to you in detail how. Okay, so what I want to do is, since most of you don't obviously know the physical mechanisms that underlie what I'm going to discuss about fusion, I'm going to dwell on that. So I'll spend until the break or longer discussing some phenomenon that you may be familiar with in some visceral sense, but in fact may have never thought of in a scientific sense. And it's that work that led me to this problem of planetary or solar system formation. And I hope to be able to make that connection. That connection itself is very strong from the perspective of what's called surface phase transitions. The connection to the astrophysical realm is made by me in a rather heuristic way, which involves ingredients of phenomena that you know very well, and I just learned when I was here in 2008. And as Axel said, what I'd like to do is ultimately implement some of the things that I'll tell you about in a large-scale numerical simulation, which I need collaborators for. So as Axel said, I'm visiting here for 5 months, just came here last week, and I visited the first time in 2008. And what preceded that was my relative ignorance that I'll describe here in some detail. There's a course called Physics 667, Special Topics in Condensed Matter Physics, which is a great course to teach. We have these at various universities in the States. It's basically, if you get to teach the course, it's whatever you want to do. And the great thing about that is when you don't know anything, you have a group of students who are eager and energetic, and they think you know something, and you say, actually, I have no idea about this. You guys can teach me about it. And so for 12 weeks, I try to learn from them. And at this time, there was a paper that I had been stewing over that's now, since 2005, that was published in AFJ, having to do the remnant ferroelectricity of ice. So does everyone know what ferroelectricity is? Okay, so so it's the electrical version of ferromagnetism. Does that help? It means that there's some finite residual orientation of molecules that have a polarizability that's directional. Okay, so there's a claim by a group of people who used to be near me when I lived in Seattle, at the Pacific Northwest National Laboratory, DOE laboratory, that if you do certain experiments with ice at low temperatures and even at rather high temperatures, there's a residual orientation of the molecules. Okay, so ice is made of water molecules, which are polar, and their argument is that instead of there being a random orientation, which has been understood for a long time, there's a permanent orientation. And moreover, because of that, you could imagine, and that's all they did, is imagine that you could enhance the agglomeration of matter from the molecular scale in an early solar nebula. Okay. And this would be important. Now, they had no calculation that connected their measurements, which I happen to believe were wrong, and I still do, to agglomeration. but it got me thinking about that because I do work in ice and various aspects of ice. So I said, let's try to understand what they did, and we started to dig into the literature. And that was the spring of 2008. I came here in June of 2008, and after the whole spring, I'll tell you, we read papers and we didn't know anything because none of us really were versed in anything but the condensed matter physics of ice, and we didn't really know in the literature, especially in the astrophysical literature, what's lore and what's fact and what's fiction and what's hearsay. And that's a problem because you read a lot of papers and you repeatedly see this is said, and then you need to go to Axel and say, is that true or is that just rumor? And he says neither. So at the end of this, I found this quote, which was from a well-known astronomer that characterized our feeling, which you can all read, but this may not be true for the particular context that was given in 1964, but it was certainly our feeling still at the end of 13 weeks of trying to understand what's the number density of particles at a certain distance in a nebula, what's their size, distribution, and so forth. Because most of that information comes from numerical models. It's very hard to do active probing of a disk that's accreting. And so that was the state of things when I came here. And then I tried to slowly piece together a picture which had some physical basis and ultimately a heuristic connection to what happens in disks. Okay. So let's start with something that can be useful. That's ice. Everyone's familiar with phase diagrams, right? This is a semi-log plot of the water phase diagram. Ice, water vapor, liquid. I encourage you, if you are interested in ice, there's this website that's maintained by Martin Chaplin at London South Bank University is unbelievable. It's incredibly thorough. Yeah.
What is it? Is it water? The diagram for water?
Yeah.
Pure water.
That's right. That's right. Which is another matter. But so this is pure water, and these maps of the stable phases of matter, whether it's water or something else, are essential guideposts. They're usually fragmentary in terms of their understanding empirically. No one can ab initio start with the potential of a system and predict all the aspects of a phase diagram. But the great triumph of early theoretical condensed matter theory by van der Waals was to explain the critical point. Out here you can distinguish between the liquid and the vapor phase, and the van der Waals equation of state is the wonderful thing that does that. It was his thesis work, and in fact Planck surmised that there was a critical point along solid-liquid coexistence, and which is a great lesson for students. Because if you're Planck, you can say things and it'll be wrong, and people then go looking for them, and that's what Bridgman did. Percy Bridgman, who then won the Nobel Prize for his high-pressure work, developed high-pressure apparatus to seek the critical point up here that was predicted by Planck. And what he in fact found was other structural phases of water or ice, the polymorphs of ice. Okay. He squeezed it harder, he in fact found different structural phases of ice. And we're used to, on this planet, thinking about this region of the phase diagram. When we talk about what happens in a nebula far out, we're really talking about low temperatures, and I'm going to talk about collisions that occur at high pressures. Okay, so the phase diagram becomes important there. Okay. All right, so let's ask what happens when we walk along coexistence. And the important part of this is that I need to motivate the structure of surfaces that are essential when you have bodies colliding in the nebula. Okay? So I need to know a lot about what the surface looks like and what are its phases. Okay? So that's a surface. So it has a phase behavior that's extensive with area, not volume. Okay? So I'm going to be talking about mostly lower dimensional phase transitions. Okay. So first I'll discuss what are called equilibrium transitions, things you're familiar with, but in lower dimensions. And then I'll talk about disequilibrium transformations. Okay? So the two ones I want to focus on are surface roughening and surface melting. There's a whole host of zoology of things that people look at. And both of these are the ones that are relevant to the study that I'll describe for the nebula. Okay? Some definitions. Here's a cartoon definition of the two types of surfaces that we see existing on solid matter. Faceted orientations. So you can imagine that if you were to take steps that are molecular scale, a faceted orientation is smooth on the scale of the lattice parameter. And a rough orientation has got a hill and valley structure on that same length scale. Now, importantly, this surface and this surface behave entirely differently when you're talking about how they grow, what they look like, how adsorption works on their surfaces, what's the nature of the disorder, and so forth. Okay. And so people have been studying both of these and their coexistence. This doesn't really come out very well for whatever reason. This is the same crystal. It happens to be a piece of ice. You're looking down what's called the C-axis. It doesn't really matter, but it's a particular axis of the lattice. And what you see, if you can see it better, actually, is it just me? Or is it, no, it's that image. So this crystal is faceted, okay, along these orientations, which are called the prism planes, at low temperatures, okay, and high pressures, because ice floats on water. It's a coexistence at low temperatures and high pressures. This is the phase diagram from Minoru Maruyama's work. And as you increase the temperature and decrease the pressure along coexistence, you notice that this thing which is faceted becomes rounded and smooth. Okay? And in fact, right here, at this temperature, the prism orientation becomes molecularly rough. So that is an observation of the roughening transition, and it depends on the parent phase that the solid matter is in contact with. So in this case, the parent phase is water, and you see that at minus 16 degrees and 160 megapascals, this particular orientation becomes molecularly rough. The system that we originally studied a great deal and have excellent quantitative understanding of is helium-4 in contact with a superfluid. And you can see just qualitatively, as you go towards the lower and lower temperatures, a single crystal becomes much more polygonal. Okay. By parity of reason, if you take this crystal and you increase the temperature, the higher order orientations become molecularly rough. So the roughening transitions of all these facets manifest themselves as the temperature increases. Okay. Now, if you're not familiar with this stuff, the reason people want to study this, it's very difficult to hold matter near absolute zero, but the nice thing about it is that you don't have to wait for equilibrium to be reached. Okay. Because there's essentially no latent heat of helium-4 in contact with the superfluid. There's nearly infinite thermal conductivity, and so forth. So literally, as you change things, it's in equilibrium in nearly real time. So that again is in contact with a liquid, another material. If we look at the vapor phase, here's a negative crystal of ice, and here's the same facet that went rough at minus 16 degrees in contact with the liquid phase, and in the vapor phase, it's a higher temperature. Okay. Now, what's happening is that at very low temperatures, the cost of taking a molecule or atom out of a facet and putting it on the surface, the enthalpy of fusion, is rather large. Okay? But you don't get much from the entropy of configuration, right? Because you just put one atom on the surface. So the competition between entropy and energy is such that energy wins at low temperatures, and as the temperature reaches the critical temperature, the entropy wins. Okay? And the surface roughens. And there's a correlation exponent of the surface, and so forth. All right. So that's roughening. Right? So we need to know, for example, for crystal growth, or for what happens when two particles are going to collide, we need to know the state of the surface before the collision, if we're going to say something about the state of the surface during the collision. So another influence on the surface of all material is called surface melting, which is also a surface phase transition. So I want to motivate this at several levels of detail, and then I'll just state results and use them. So, has anyone seen this object, droplet of water? I just was going over to the wrong seminar room, and I experienced those things. So here it's a sphere. This is the point at which I ask people, can you tell by virtue of nothing more than the fact that I told you it's a sphere how big this is?
It should be capillary size.
Sorry?
It should be capillary size. So
The capillary size. Okay. So he's right. So what is that?
it is, roughly speaking, sigma divided by G something.
Something like that, yeah. It's divided by rho g, the square root of that.
Rho G R equals sigma something. Remember correctly.
Something like that, yeah.
What?
I don't know. I mean, it's good, but usually it's the students I ask. But that's the surface tension. This gives you the length, which is called capillary length. And if, so that's the balance of surface tension against gravity, and if the object gets bigger, then the field of gravity is going to distort the object, it's no longer spherical. Okay? So so as long as the size of the object is small in this, which is a few millimeters, then it'll be a sphere. If it's bigger, then it'll bulge. Okay? This is all by way of motivation. And the capillary length, of course, depends on the material, right? So if you imagine mercury droplets on glass, when they're this size, they're actually deformed. Okay. So now we can say, well, why is it that mercury beads up on glass? I mean, has anyone done this experiment? Some people here haven't even seen a mercury thermometer before. Much less So if you happen to by accident break a mercury thermometer, if you find one, you'll see this. Okay, so you could ask yourself, why is it that mercury beads up rather than spreads out on glass? Because it does, right? Because that's the observation. And now you're going to say something, well, he's busy writing something. He's going to say something about surface tension, right? Sorry, someone was talking about you behind your back.
Just with water, nothing else.
Okay, so there's an angle here that a droplet sits on a substrate with, which is called the contact angle.
Right.
And this is the Young-Dupre equation. And you can imagine by changing the surface tensions, you'll change the contact angle. Okay, and this is the standard discussion for the contact angle of all materials. And now I could ask you, well, where does the surface tension itself come from? And you say, well, you just write it down. It's gamma. It's an energy per unit area or force per unit length, okay? But there's more to it, right? What it is the effect of long-range interactions, just like gravity. Okay? So if you take all the volume-volume interactions between this liquid, this phase here, and the underlying substrate, okay, those that are extensive with volume, okay, and you throw those away, those that are left over that are extensive with area are the surface tension. So that, in fact, the surface tension comes from all the long-range volume-volume interactions between all the molecules in the system. So if the potential was like gravity, and you knew that was the only potential, then you could calculate the leftover energies that are extensive with the surface area. Now, in this case, this equation turns out to be wrong because those interactions aren't described explicitly. Okay? So now I want to tell you about what happens to the surface of a solid phase in analogy exactly to what I just told you with respect to wetting. So imagine that I take, say, a piece of ice, and I cleave it along my favorite orientation. I bring it in contact with the vapor phase along the sublimation line, okay, and so it's in coexistence. And then I walk towards the triple point from lower temperatures, okay. I ask what happens to the surface, and what I observe is that there's a temperature at which there's a thin film of water that disjoins the solid from the vapor phase. Now, remember, it's a phase diagram, and the phase diagram, or at least part of the phase diagram here, right? Here's the solid phase, the vapor phase, the liquid phase, right? There's only two phases allowed here. Right? That's what the bulk phase diagram will tell me. And yet here I have a third phase that's disjoining one from the other phase. And you might think that violates Gibbs phase rule, but the Gibbs phase rule is not at all violated because once I introduce a surface to the problem, I have a new pair of canonically conjugate variables. Okay. So surface energy extensive with area. And what I want to think about is that this is just like the glass underneath the mercury. It just happens to be made of the same material here. Yeah?
Just to understand basic thermodynamics. When we discuss, for instance, vapor liquid phase transition, a very intuitive way of doing that is through the Maxwell construction.
Yeah.
And the coexistence gets very nicely described by that.
Yeah.
So can you also do that in your case? Can
Yeah.
you write, free energy Maxwell construction? That's a very basic, nice argument. The one should get the coexistence phase.
Yeah.
Can you do that?
For both phases, okay? Right? So I can make a Maxwell construction, but in the Maxwell construction, I've got volume, okay? So my free energy is extensive with volume, okay? And here now I have an area. So I have a new access to my Maxwell construction.
That's right.
Yeah.
It's an energy argument, so it should work also in that.
It absolutely does. It's just that now I have another pair of canonically conjugate variables. Okay. So the Gibbs free energy, right, which is internal energy minus the temperature times the entropy plus the pressure times the volume, now has another term, which is plus surface energy and area. Okay. So now I've just extended the dimension of my Maxwell construction. Okay. It's 5 minutes to 2. All right, if you're going down the hill, go. Okay. So the mercury on glass, right? The reason the mercury sits as a bead of liquid on glass is that its self-attraction is greater than the attraction to the underlying glass, right? So the polarizability of the mercury is larger than the polarizability of the underlying substrate. So you can imagine, again, if the potential was a gravitational potential, so here's my substrate, here's my droplet, okay, so the self-attraction of the mercury is greater than the attraction to the underlying substrate. Now, imagine if I could change this material, and I just slip another substrate underneath my mercury, okay, and I make the polarizability larger. If I hook this thing up to a reservoir of mercury, okay, little tube, and I slowly dial up the polarizability of the substrate, then I'm going to build a film here, right? I'm going to pull the liquid out of this bucket, and it's going to be attracted to the underlying substrate and build up a film. The contact angle is going to go to 0. And that's driven by the volume-volume interactions in the system, the adsorbate-substrate interaction in the system. And so it is also in the case of an interface between a solid and its vapor phase along the sublimation line. As long as the polarizability of this is greater than this is greater than this, or the polarizability of this is greater than this is greater than this, then this will be attracted with a greater force than this will be. Okay? And a thin film of liquid will be stable at the interface between the solid and its vapor phase. And as the temperature rises, this film will get thicker. And this is a generic phenomenon. You see experiments here, some of the first beautiful experiments done by Joost Franken and his group in Amsterdam, of the lead 111 surface looked at by ion backscattering. Lead melts at 600 degrees, and you see the number of molten layers diverging as you approach the melting temperature from below. This is Michael Elbaum. Sorry?
Second order phase transition.
Sorry?
It's a second order phase transition.
There's a subtle issue about whether or not this is of the universality class of a Kosterlitz-Salas transition. There's a hysteresis.
Now that's a line of these points. That's much harder.
Yeah. If we withhold for the moment the nature of the critical point, okay, I'll come back to the issue if we have time. Okay, the Ehrenfest classification of phase transitions is sort of useful in some pedagogical sense, but the point is that this transition itself is what underlies the first order phase transition of the bulk, okay, which I'll just describe in a moment.
Your system effective dimension is 2.
That's right. That's right. So let me just come back to that when I develop this. Okay. So there's a relationship which I'll develop here between the film thickness and the actual temperature, which is scaled to the bulk melting temperature. Okay. That's the reason this is called surface melting, because the surface melts from inward, okay, and diverges at the melting point. So let's motivate how we think about this, and let's talk about something that everyone is familiar with, and then I'll just refer to this in the context of what happens in the melting transition. Okay. So imagine I've got an object in an external field, okay, at some temperature, okay. What about hydrostatic balance? Okay, so this gets to the question of the dimension of the system. So this is a mean field theory for deriving the hydrostatic equation. Okay. Normally you derive the hydrostatic equation by thinking about a force balance on a layer, right? But we call it thermodynamics because you should be able to derive the dynamics from the thermodynamics.
You cannot use the Wittich theory in 2 dimensions.
The upper critical dimension is bounded from above by 3, and so let's come back to that. Okay. In some sense, it's irrelevant. So here's the chemical potential of my object. Okay, in an external field, it has a bare chemical potential, which would exist at this temperature and pressure in the absence of the external field. Okay, and it has some field energy per molecule, which you're familiar with, mgz. Okay, and the chemical potential has to be invariant in coexistence, and so I can simply write this expression in terms of a Maxwell relation. That's the volume, and that you know, and that's the hydrostatic equation. So, we have one person who doesn't believe in the hydrostatic equation, which is fine. That's his prerogative. Okay.
I'm skeptical.
Okay, I refer you to Landau and Lifshitz. Okay. They're tougher to be skeptical of.
But he was working in Wall Street.
Sorry?
Landau, you mentioned.
Yeah.
He was using Wall Street.
The point is that this is two dimensions. This is between 2 and 3 dimensions. Okay. It's the surface of a 3-dimensional object. Okay. So we're between 2 and 3 dimensions. All right. So what you have to do is the full RG theory and show what the upper critical dimension is, okay, which for this system is bounded from above by 3. Okay. So it's a 3-dimensional system, but the surface itself, when the transition is initiated, is more 2-dimensional than 3-dimensional.
In a sense, you are saying that fluctuations are not so strong to destroy long range objects.
Yeah.
That is your point.
Yeah.
Could you remember what is sigma actually?
Sorry?
Sigma, what is it?
I haven't told you. Okay. So what I wanted to do was to tell you something you already knew. Okay. Which is the hydrostatic equation. So everyone here knows the hydrostatic equation, and I derived it from a mean field theory. Okay. And so now I want to talk about the interface between the solid and the vapor phase, and ask if we can explain the existence of these liquid films, okay, which are experimentally observed. Okay. And the idea is that the chemical potential in the presence of the external field, and the external field is the set of long-range interactions which are attracting the liquid to the underlying solid. Okay, that's this. In the previous slide, it was mgz. Okay, now it's something else, right? And so the chemical potential of the liquid in the absence of that field, okay, plus that field has to equal the chemical potential of the solid phase. Okay. And that's a mean field theory because I don't have the fluctuations that are coupling that. All right. Now this thing, okay, comes from the long range interactions. The simplest way to describe it here is the attractive part of the van der Waals interaction. Okay. So
is it similar to van der Waals forces?
So the attractive part of the van der Waals interaction. Okay, I'll show you the explicit expression, but this thing here is called the Hamaker constant. So it's the lower dimensional version of the strength of the pair potential for the volume-volume interaction. Okay, and it turns out that I can relate it to things like the differences in the wet versus dry surface tension and something that's on the order of a molecular scale. So that's what this thing is.
So this is distance between molecules of length 3 plus something.
So the correlation length only comes in at very short range. This is just simply a length scale that's the molecule size or the atom size. Okay.
What is it actually? It is if you build correlation function of density, it is scale of this stuff.
No. Let me just show you this on the next slide. Okay. But in the same vein, okay, equilibria is reached when the chemical potential is uniform, and so the Maxwell relation allows me then to relate this film thickness to the reduced temperature. Okay, so the reduced temperature is just this thing. All right. Now, what else do I want to say about that? Probably nothing. Except for I will say, here I have a liquid film that exists at some temperature below the melting temperature, okay, along the sublimation line. Okay. That film diverges with an amplitude and an exponent as I approach the triple point from below. Okay, so it's the way in which all solid systems in equilibrium reach coexistence, three-phase coexistence. Because you get an arbitrary, because that's the definition, is that you have an arbitrary amount of all phases at coexistence, and as the temperature approaches the coexistence point from below, that's how you get bulk water coexisting with bulk ice and bulk vapor. It's also the origin of the asymmetry between melting and freezing. If I take a bucket of water, I can deeply supercool it before I nucleate the solid phase, okay? Because there's an antagonistic energy penalty for creating the surface between the two phases. Okay? But you cannot superheat a solid in equilibrium, okay? Because you already have liquid existing there. Okay? So that's the origin of this term surface melting. So all solids do it. Okay? Now, so the truth is this. You asked about the sigma. I wrote the Hamilton constant glibly. Okay? A Hamilton constant turns out to be a limit of the full frequency dielectric response in the system. Okay? So you have to know what's the polarizability as a function of frequency of the solid phase, the liquid phase, and the vapor phase. And I'm not going to discuss that, except for I'll just tell you it's a long story. Sorry? The frequency-dependent polarizability. Okay? And it goes back to Dzieloszynski, Leszczyński, and there's a long list of stuff that deals with getting this all correct. Okay? Okay, fine. Now I'm going to talk briefly about disequilibrium transitions, and then try to connect this to what happens elsewhere. Okay. So now systems are often not in equilibrium. They're growing or evaporating, and that changes the structure of the surface as well. You can imagine that as I bombard a surface with more and more molecules, that there's a transition again. At very low growth rates, you can build up a molecular structure on a faceted surface. But if you increase the flux rate, then eventually it becomes molecularly rough. Okay. That's also a phase transition, a disequilibrium phase transition. And you can show that it smears out this equilibrium roughening transition in a way which depends on the growth drive. So now, all this is by way of saying that when one thinks about this stuff I've just been talking about, and one starts to ask about what happens when things collide, then there's a natural context to begin asking this question: what happens when two things whack into each other? Okay. So the same argument, I want to think about this as a state theory, a thermodynamic state theory. Except for what I didn't describe to you for this d equals delta t to the minus 1/3, okay, pressure was not an important contribution. It turns out because of the compressibility, it's about 1,000,000 times smaller. But if I'm talking about gigapascal pressures, then it becomes important, okay? So I put pressure back in, and what I want to ask is when two things collide, some fraction of the translational kinetic energy is going to go into changing the local chemical potential of the bonds at the interface shared between the particles. Okay? And it will lower the chemical potential of the liquid relative to the solid phase. Okay? You can think about that as crudely as damage. Okay? And I can think about this: if the sound speed and the thermal diffusivity are right, then there's just a region that is equilibrated, okay, to the local temperature and pressure. And when I do that, I then get a change in that expression. Okay, that not only is the existing disorder going to give me some liquidity, but the pressure is going to give me some liquidity. And I can imagine as the temperature rises towards the melting temperature and the pressure towards the melting pressure, that the damage energy is going to intervene and make this liquid become rather thick. Okay? So I've just rewritten that. And it turns out when you put in the numbers for ice, which is something I'm interested in, this is very near the divergent limit, and you can get a relationship between the film thickness, the pressure, the temperature, the contact radius, and the collisional energy, and this has one free parameter. Okay? And so everything that I want to talk about has one free parameter, which I really don't know. I have one constraint of it, and this is an issue which is an ongoing issue, but I'll discuss it in some detail. Okay. What this is the fraction. Yeah.
What is this high-speed collision in comparison with what? What kind of, what does it mean, high-speed collision?
It means, in my case, no more than that the pressure term is important. Okay.
So compared to the sound speed in the solid, for example.
Well, so that's not really relevant. The issue of the sound speed in the solid tells me whether the region over which the collision is adiabatic.
Yeah.
Okay. So the actual pressure that I care about is whether I'm going to be pushed towards a phase transition. Okay. So it matters what the phase diagram is that I'm talking about. So if the pressure becomes, really large, okay, then I'm going to find a high density phase. Okay? Now the pressure may not be large enough. Okay. The collisions have to be of a certain kinetic energy for the pressure to be large enough so that I reach a phase transition. Okay. So the idea is that I want to keep the pressure in and then examine that question. Okay. And the thing that I don't know, because I have it fixed in my mind that two things are going to collide. So imagine I throw clay against the wall. I've got some translational kinetic energy, and that's transferred into the anelasticity of the clay. It deforms, right? And the whole thing deforms. Okay. Now I have solid matter, right? So some fraction of the kinetic energy. So if I throw lead against that wall, if I throw the lead hard enough, maybe someone else could do. You could, put a hole in the wall, right? I want to ask what happens momentarily, right at the interface between the particle and the wall. Okay, if it doesn't shatter, which is of course another matter. Okay, and so I want to say that some fraction c of the kinetic energy is going to be transferred to the interfacial region to lowering the chemical potential of the liquid phase. Okay. All right. So what? That may be what you're thinking. Yeah. So what? The reason I labor all this stuff is that every solid that we know of is finite. Except for the one that we dream up of. And all solids are finite, they all have a surface. Okay? And the surface is usually what interacts with the rest of the world. Okay? So much of the behavior of the material depends on what the structure of the surface is. And so there's a lot of examples that we worked on. You can imagine that the way in which molecules attach to the surface of a crystal depend on the structure of the surface. I've already motivated that. It does. And the thing I had in mind when I started working on this particular problem is a project that had to do with the charge transfer in thunderstorms and how you get a polarization in a thunderstorm. And this involves collisions between particles moving in an updraft and particles falling. Okay. And it turns out you can't get this polar structure without active glaciation inside of a cloud. Okay. All right. So now this is the entree into the problem that I wanted to start to address.
Yeah, but you do not show any free energy. So you show a plot of your model. You end up with the free energy.
Sorry?
You end up with the free energy with your model.
Chemical potential. I expand the chemical potential and look for extrema.
Yes, but
That's the free energy.
That's right. But how does this free energy develop the expansion of your Bayer mass? Let's call it your T minus T over T.
Yeah. So there's two contributions to the free energy.
Yes.
So there's the bulk free energy, which finds a global minimum at zero film thickness.
Yes, it's a function of temperature. Can we see that?
The free energy is the free energy I minimized, right? that gave me d is equal to delta t to an exponent. Okay? So there's two contributions. I wrote the mean field theory, which has got the bulk contribution plus the interfacial contribution. You know from this that the bulk one has a global minimum at 0 film thickness, which means if there's going to be a film thickness existing, then it's the interfacial free energy that decreases as the film thickness increases. And that reaches so those two things balance. I minimize that, and that's yeah. So that's what it is. So there's this book by Phil Armitage on planet formation that I've been reading. So you know that nebula forms by the collapse of a large cloud. It's rather quick. Residual angular momentum creates a disk. And accretion and primary planetesimals form in about 1 million years. And then there's a slow accretion onto the central star, and then eventually a clearing by a photoevaporative wind. And people believe that in several million years, you need to make planets that are big enough to withstand this process. Otherwise, the material from which the solar system formed is swept away. Okay? So this is the problem that yeah.
To ask your own question, which part of this is lower and which part of this is well established?
Yes. You know, so this all has ingredients that have lower and are well established. So the actual time scales, most of the time scales that we're talking about are constrained actually by geochemistry, right? And the dynamics are models specific. And so then it depends on who you ask for their models. And I can tell you that all of those people reviewed my paper, which is why it took so long, I guess. But I would say the principal experimental constraint, if you want to call it, is geochemical, right? And that only puts a rather large bound on things. Okay. So the thing that sets the stage for the collisions is that the dynamics of the gas in the disk are slightly subkeplerian because of the central star. Okay. So that's this term here, okay? And so in the thin disk approximation, you get a slightly subkeplerian gas velocity, okay? Yeah. So of course it depends on the model, but for example, for n equals 3, the azimuthal velocity is 0.996 Keplerian velocity. Okay. So this is, I believe this is first pointed out by Wiedenschilling. I may be wrong, but this is my understanding of the paper by Wiedenschilling in 1977. And the point of that is that a particle that's big enough and that's moving in the disk will see a headwind because of this subkeplerian velocity. So just like you're driving down the road and and a bug is going to come and hit your windshield. That means, and this is what Wiedenschilling pointed out, is that by conservation of angular momentum, it gives up some angular momentum to the gas, and it's going to be lost to the central star. Okay. So it's that process that's the focus. I think I will not belabor this, except for to say that you could write down in the equations of motion for the particles inside of the disk. And a thing that makes it interesting and I think very challenging from a totally different standpoint, but something that impresses me, is that you go from the regime in the inner nebula where you have Stokes drag to the regime in the outer nebula where you have this Epstein drag, which makes for a challenge numerically. So the Stokes drag is what you're just familiar with when the particles are large relative to the mean free path, but when the mean free path is large relative to the particles, then you have another type of drag. Okay? And that's a challenging problem in fluid mechanics. So the upshot is the following. Okay, so this is the problem. It's not my problem. It's the problem stated that I entered into this with, and this is just a different version of the plots by Wiedenschilling of the inward radial velocity scaled by the Keplerian velocity relative to the Stokes number, which you can think of. It's just the ratio of the friction time to the rotation time, but you can think about this as particle size. Okay? So as the particles, if the particles are small, they're acting like gas. Okay? And if the particles are really big, they could give a hoot about what's... They don't care, right? But as they grow, okay, then they start to see a bigger and bigger headwind. Now, this is worth thinking about a little bit, because the picture in the community is that it's very easy by van der Waals attraction, right? Because any 1-2-1 system attracts under van der Waals forces, forgetting any other exotic thing, okay? So dust balls in the corner agglomerate, right, by these long-range attractions. And so the picture is it's very easy to build up matter to centimeter scale. And there's a huge group in Bloom and Verm who've written tons of papers on this, how you build up particles. Okay? And so that's not necessarily that difficult, okay? But it's a very peaceful process, and it's, you know, molecule by molecule or particle by particle. And as the particles get bigger and bigger, they move inward faster. And yeah.
And in principle, turbulence should affect strongly transport of particles. So, for example, if you compare this Stokes number with the Stokes number determined by the ratio of Stokes time to Kolmogorov time scale, it's viscous time scale turbulence.
Turbulence, yeah.
Yeah. So.
Okay, so that. Yeah. Let me come back to turbulence. Okay. This is the as usual the bugaboo in such a problem, and I have no solution. I have no solution to this problem. But this problem is called the 1 meter bottleneck for accretion. If you happen to be familiar with it, I wasn't a few years ago, but it's just because the calculation that Wiedenschilling did said that if you begin with a 1 meter scale body at 1 AU, it's lost to the central star in 100 years, okay, which is too fast. So the idea is that you could have a factory creating particles, building them up, and they're just it's a conveyor belt that they're lost continuously to the central star. And this is very interesting because, as we know, there's a solar system, right? And so then what? Okay, fine. There was a solution to this, although I have no idea about priority. There's a paper by Goldreich and Ward, which is another story. Okay, the idea is that the particles set in their paper. Okay, which this is all I'm going to say about Goldreich and Ward. They have particles settling to the midplane. Okay? When the particles reach a critical density, when the number density of particles in the midplane gets to a critical value, then you get gravitational collapse. Okay? When they do the analysis of that, then the size scale jumps over the bottleneck. Okay? So they had done this, as far as I understand, before Wiedenschilling's it is before Wiedenschilling's calculations. Almost immediately, though, there was some controversy, there's an interesting exchange in the literature and so forth. But their solution is that you jump over the bottleneck, or the post hoc rationalization of it, by nucleating particles that are large enough so that they don't care about the headwind. Okay? That's their argument. This was immediately criticized because the argument is that the Richardson's number, the shear Richardson's number, always maintains the density below the critical value. Because in each stream you have a vacuum, you have some gas, you have particles, and that they're always being resuspended. Okay, that's the argument. And there's recent work which involves Andrew Uden. He's been working on this. But that's all I'm going to say about those guys. Okay. So now we're getting close. Let me just tell you the ingredients of my diagram. So the ingredients are: I need to have the phase diagram. Okay. I hope that's evident. And now I need some constraint on the fraction of damage. Okay. This I have no ab initio calculation for. Okay. I need to know what happens during the collision, because what I want to do, obviously, is I want to grow matter quickly. Okay? So the idea is that I'm going to get a momentary collision. There's going to be liquid or high-pressure polymorph shared between the particles. And before they rebound, that has to anneal or freeze. Okay? So that there's fusion between the particles. Okay? And then I need to put it into a disk. All right, so take my word for it that these guys at the Paul Scherrer Institute have a very good idea of the nature of the transition at high pressure and low temperature. There's a whole controversy about what happens for ice. There's something called a high density amorphous phase and a low density amorphous phase, and so forth. Come talk to me if you're concerned about that. I can make liquid, okay, for various speeds and various assumptions about this C parameter. Hundreds of microns of liquid shared between particles during a collision. Okay. Now, here we go. Here's the velocity of the colliders. Okay. Here is I'm going to collide a particle with a meter-sized particle with a particle of this size. Okay. Now, ignore all of this just for a moment. Okay. This line here is the line determined by Shokshi. Okay. Has anyone read this paper? Shokshi. Okay. I have. So this is a beautiful paper, and it describes basically the agglomeration of dust balls. Okay, it's wonderful. So small particles, they even do the surface waves and so forth. Okay, in this area, as I discovered from reading all these papers, this is the paper that people refer to for agglomeration of particles, the theoretical paper for it. And the idea is when the collisional energy is small relative to the surface energies, then you have sticking, otherwise you have bouncing. So the Shokshi limit is that anything below this curve, things stick, and anything above this curve, they bounce. Okay? Now, if you look in papers authored by members of the people who contribute to the pencil code, and you ask about root mean square collisional velocities in this, we're talking about meters to tens of meters a second. Okay, so this limit is not going to get you there. Right? Now I'll just say, if you assume that, and you have a relatively sophisticated model, most of these have been developed by Kuzi. If you assume that everything that hits sticks, then this bottleneck problem goes away. Okay? But there's no based on this theory, you can't assume that. Okay?
And that's confirmed by the experiments in Tübingen, where they do that, or in Heidelberg, right?
This
The
curve.
country limit, yeah.
Yeah.
Bloom,
Yes.
Bloom, it's in
Bloom and Vernon.
Bloom,
Yeah.
Right. Good. Yeah.
Right, but we're talking about
Right.
pretty
Yeah,
small
Must be
collisional
close,
speeds.
at least. Yeah.
Yeah.
Good, yeah.
So they have confirmed shock C, but
Yeah.
the boundary itself is not very sharp.
Uh-huh.
Okay. So now these two curves are mine. For 10% and 20% of the kinetic collisional energy going into damaging the surface. Okay? That creates my film thickness. I calculate the pressure and the temperature. I do the collisional dynamics, and I ask whether or not it bounces before it freezes, and so forth.
Wasn't there a gap in between somehow? Or
So
is there-
I'll come back to that.
Right.
There is a gap. So,
What are the red dots?
sorry?
What are the red
So the red dots. So the red dots are the reason I have these numbers, okay? And those are experiments. So the red dots come from these experiments here by Higa, okay? And Higa, these are the most extensive experiments that I can find. And what they did was so this is all for ice. They took ice balls and they launched them at an ice wall, okay? And they watched whether or not they bounced or shattered or stuck, okay? And this is my upper and lower bound. It comes from their experiments. Okay? That's how I chose 10% and 20%. That's all I know about. If anyone knows about more experiments, I would really like to know about them. This is for ice. It's obviously harder to do for inner solar system materials, which have very high melting temperatures. And to be a harsh critic of myself, the problem with these experiments is that they're at very high temperatures. I mean, 240 Kelvin. Okay. Yeah.
Did we have the same curve for some dust, not just for water? Because in planetary disk we have not just some water or ice or
Yeah.
vapor, some dust, but that's not.
I think I made a comment about that about a minute and a half ago. I would have no basis to compare them, those experiments. Dust, first of all, the collisional speeds for the dust are down here, at least in the experiments. And the material for the terrestrial planets is a high melting temperature material, right? And so a high melting temperature material, if you're going to test this theory, would require a whole set of other experiments, which don't exist at these collisional energies. Okay. So the dust experiments, there are a lot of dust experiments, but they tend to be in these low velocity regime.
But you also expect to have ions to play a role in this type of process, really, no? Because surely we expect that they will have completely different, they really can change the way this kind of long-range interaction. Because your temperature there,
Did you say ions?
ions, yes.
Yeah.
So that should, I mean, I guess that the important ingredient.
Okay. No. And one of the things you show, so we've worked out the quasi-steady quantum electrodynamics of intrinsic ions in ice. Okay. Put that into this kind of a formalism. Okay. Calculate the Debye length in the ice, because ice has intrinsic ionization defects and Bjerrum defects. Yeah.
We know from Raman spectroscopy that these water have some other molecules, and then once you get some temperature from the sky in the middle of February, they can get very you will immediately have big resonance and they will definitely be important. I mean, that's not the question of pure water. The question you have also molecules. You have methane, for instance, and then you have some radiation there. They will immediately probably you have probably dissociation of these species, which will create other additional activities.
I think we should postpone detailed questions of that level maybe to after the talk,
Okay.
because otherwise it will take too long. Can you do that?
Yeah. I'll just say, yes, we're not complete idiots. Okay, we know about we know about the adsorption of ions on the surface of ice. Okay, but the point is that the pressure of the collision becomes so large that this completely kills the effect. See, the exponent in my relationship is gone. So whether or not there is a whole zoology of interactions which are associated with the surface structure, they're killed. Okay, when the collision energy becomes gigapascals. Certainly, there is no way that I have treated all the chemistry that occurs in a disk. That's I can't do that. We know that they exist, and you know, we crawl first, we walk later. So this is, according to this, a reentrant sticking phenomenon. Okay? Shokshi at low velocities, nothing here, a regime of sticking and then bouncing. Okay. Now we are way over time. So it's Hertzian dynamics. I have a collision time which is weighted by the damage. I have a freezing time. This is the bound I more or less just showed you. If the collision occurs in this domain, I would expect them, according to this, to stick. If the collision energy increases, then the recoil time is so fast that you don't have time to re-anneal before it bounces. Okay? If the collision energy is so small, then you don't have enough energy to damage the interface to create liquidity to do this at all. Okay? So that's the argument. Okay, everyone's tired. So alpha. Okay. So this is an enhancement of midplane density due to turbulence. It's a scaling argument, which has to do with the Stokes number and alpha. Okay. As turbulence gets larger, you don't have a high density of objects to be fusing with, and as alpha gets smaller, then the midplane density gets higher.
And this Stokes number is based on Kolmogorov time scale or on the rotation?
Rotation. Yeah. It's crude, okay? I'll just say, at the point of coming to having a theory for how things may fuse during high collisions, high energy collisions, I finished there and I wrote a paper. And the people said, so what? You know, put this in some context, okay? So this is the back of the envelope context. Right? So now the idea is you have a drifter, it's coming in and it's colliding with particles in the mid-plane that have one size, okay? And if they meet this criterion, they fuse. If they don't fuse, okay? So just the range of alpha used, and I'll just convert this. This is the size of the particle, which you see becomes of order of kilometer in a few million years. Okay, and this is its drift trajectory. Okay, so again, the thing I am interested in is ice. So here's a particle beginning at 7 AU, low temperature at 3 AU, and you can see this is the range that I showed you before for sticking. Okay, and these are the alpha ranges, and you see that the particles settle down to a few tenths to a tenth at most as they drift in and grow. So if you put this into a very crude disk model, which has that alpha parameterization associated with it. Even if you change the mid-plane particle size by 2 orders of magnitude or more, these numbers don't change significantly. Okay. Okay, so let me say how general is this. When I was here before, this paper was published. Okay, so these are MD simulations of silicon. So it's a high melting temperature material. Okay, but they're MD simulations. Right? And so this is silicon substrate. This is a silicon ball. Okay? At low velocities, 900 meters a second, particle comes in and bounces like a Hertzian basketball. Okay. So I was very interested to see these results because I have the problem with water, as you may know, if you do MD simulations with water, we don't know the potential. Okay, there are models for the water potential, but we don't know that potential very well at all. If you do pure water, you can do the electrostatics out to hexadecipole, but you can only do nearly zero temperature calculations. If you put in ions, okay, even in very low concentrations, there's no facility of these potentials to deal with ions because the ions induce defects in the ice, okay, and it's very hard to keep track of these defects. They live on picosecond timescales.
This is very small, right? 5 nanometers.
This is a problem, yeah. So not all the collisions in their simulations are. I can't translate this. It's a phenomenon. Okay. Now, the important thing you should know is that the high pressure phase for silicon is a beta tin phase. It's not liquid. It's another structural phase. So if you increase the velocity, okay, so now instead of 900, it's 1643. Okay, it's going to come in. Damage occurs. The beta tin phase occurs before rebound and anneals. Okay, so low temperature bouncing or low collisional speed bouncing, okay, high collisional speed damage and re-annealing and sticking. Okay, so this paper is a visualization of what I tried to describe to you. Okay, with basic simple calculations. Okay, there it is again. High collision, beta tin phase, annealing, capture.
In a similar parameter regime as your plot was?
No. I mean, my plot is ice. It's phase diagram specific.
Yeah.
I can't. I have to. This is the point. I need to put in all the phase diagrams for inner, outer, and so forth, and make equations that can be put into a code. Okay. The bottleneck problem, one solution is what I described as this Goldreich-Ward gravitational collapse. If you assume everything that hits sticks, then this bottleneck is overcome. Okay, the point is that this assumption is violated by previously understood collisional physics. Okay, at least the shock sheet physics. Okay. And so all I've done is provide a mechanism, a very simple mechanism, that provides a high collisional speed re-entrant fusing, okay? And it has, of course, a lot of assumptions and all the rest of it, which you've heard of. Okay. Thanks for your patience.
In turbulence and astrophysics, there is the effect of clustering of particles, which can strongly increase the rate of collisions. And this is clustering can be due to presence of the temperature gradient, or due to the velocity of particles becomes divergent, even if we have incompressible.
If you look at this plot, okay, sticking, no sticking, sticking, no sticking. I'm familiar with this streaming instability and the clustering of particles which could occur by vortex capture, right? I mean, you have
This
particles
is one
that-
of the effects, but
Sorry?
there are other effects.
Sorry, there are other effects.
There are other effects which results in clustering.
Okay,
Yeah.
so a view, a speculative view, is that if I have a relatively bare object colliding with another object, I'm probably up here. When I have clustering of particles, say in a vortex, then I could have low collisional speeds operating. Okay, and then I would be happy to use this whole figure. And I guess my point is that if I give you an equation which says, if these two particles are this size and they're made of this stuff, they will stick if they have this, a collision probability, then I would give you this equation too, right? And then you could see how it evolves. So my view of the clustering is that it gives you the ability to come back into this reentrant low velocity sticking. I don't know, but it's a heuristic view.
I think the main, how to say, description of contribution of turbulence is just collision efficiency. You can simply think about collision efficiency. It's increased if you take into account turbulence. Because particles concentrate in what in meteorology they name inch clouds.
Yeah, so I understand that the number of collisions per unit volume per unit time will increase if there's more particles, and if there's a
It's
high
more close,
vorticity.
not more particles, more close. If density in some places,
Okay, the number density.
Yeah.
Then fine. If I'm going to have a physical basis for whether they stick when they hit, then I believe I have to know what the particles are made of, and what the velocity of the collisions are. Now, this limit here has rather little to do with the phase behavior of the material. It's mostly to do with the fact that it has a size and has a surface energy, and it has some sound speed in it. And this does depend on what the stuff is.
Alfian pointed out many years ago that very important to take into account magnetic fields in planet formation, because they're young stars, they're extremely active, they have a dynamo, generate very strong magnetic field, very strong stellar wind, and UV and X-ray radiation. So the plasma in protoplanetary systems ionized. Even in your pitch you can show thunderstorms, they're caused by cosmic rays, ionization by cosmic rays, so unique high energy phenomena. Otherwise, that it's not relevant to planet formation this theory.
That's a very generic statement. I don't understand. I don't really understand that.
I understand. My problem, my statement is that the main mistake in your theory is that you don't take into account properties of a central star.
I mean,
Which generates very
strong
strong
for the
fine
turbulence,
radiation.
right?
Huh?
The magnetic fields may be important and very important for producing turbulence. But what if
No, it's ionization. Everything is ionized. What is ionization?
But I mean,
That's what Alfian pointed out many years ago.
one person at a time.
so, Irina, something here? Immediately to suggest? Irina.
Okay.
It's
Question or comment?
You had something?
Yes, I continue of Sasha's point.
Yes.
Actually, according to my knowledge, you cannot create a planet without present magnetic field. And my question little bit different. You speak a little bit about bottleneck effect. This effect exists only if you consider just particles of water, or what limitation for bottleneck?
It's matter. It's accreted matter in a disk. So no, it's not specific to what the particles are. It has to do with what the size effect is of the headwind. It's not the turbulence bottleneck we were talking about. It has to do with the plot I showed of the inward velocity as a function of the size of the particle having a maximum. Okay, that's the bottleneck.
Okay.
I would say cosmic rays have nothing to do with thunderstorm polarization or discharge. Well, we can talk about that. But you made a definitive statement. I think it's definitively wrong. And there's an enormous amount of evidence that says
It's something to
wrong.
discuss over coffee, I think.
Yeah.
But how about the? I mean, there's also a suggestion by Sterling Colgate about that you might have tar basically is shooting into each other, and that would stick very well. So if he was ever right, would that not also solve the problem?
As I say, you know, you can plot similar curves of the relaxation of particles if you say that everything that hits sticks. And I think that the evidence is not there for that assumption. In fact, the assumption, at least for what I studied, knowing the phase diagram, knowing the material, with all its approximations, gives you a range where sticking can occur. And that's enough to get the particles to relax quickly. So you don't need the assumption that is generally made.
Yes. Is the gap actually an issue, and could that constitute a problem? That the fact that you do have a gap in
I don't know. I mean, presumably it could. You know, with this crude model, not the crude collisional sticking model, but I think where I place it, you know, I use the minimum mass solar nebula, this parameterization of turbulence, and so forth.
You mentioned that phenomena which you discussed, thermodynamic and surface tension, somehow give a high limit of this process of coalescence. But maybe if you take into account electric charge of some particles, situation may be changed drastically, and all these small effects may be not so important. What do you think about it?
Well, so I've done you do the calculation where you put the maximum amount of surface charge density that you can. So one ion...
All particles, or just small amount? It's not the same.
Okay, I'll answer your first question, not what you just said. If you put a elementary charge on each lattice site, okay, and you do this calculation, okay, it has no effect on this liquidity that I calculate, or this annealing, or this high pressure polymorph that I calculate. It may have an effect at very, very low relative speeds, right? When you have particles that are close to each other, okay? Then you may have a rather longer range screen Coulomb effect, but I actually doubt it. That's the ferroelectricity paper that I talked about at the very beginning. The rates don't change that much for small particles, anyways. Now, ions are incredibly important, at least from the sun, very important in annealing the particles. So normally, this Bloom and Verm community, they make very fluffy particles, and they say that's what happens in interstellar media. But in fact, if you radiate fluffy particles, okay, of ice, they anneal incredibly quickly, and you have a long time for that to happen. You know, at least 1 million years. And so the density, the actual mass density of particles, at least in the outer solar system, is more like that of ice that you have in the freezer here than it is because the experiments don't do the experiments for 1 million years, right?
It's true if you number density is more or less homogeneous, but if you've got this small scale concentration, maybe situation will
Oh, I think you're right. I mean, I don't have any pretense to say I have a model which has vortices in it or any. None of that's in there. Okay. Yeah.
Yes, a short question. Do we observe protoplanetary disks like we can use?
Do we observe them?
Yes.
There are some observations of them in various stages, but but you don't, you know, obviously, you can't do an active radar probe of a distant.
I mean, we see the outer, we do see the big outer discs, of course.
But for Victoria's some observations.
This is
We observe the disk. And see this, we don't observe the disk.
Yeah, but
So can I use what you just said? Because when I sent this paper, when I sent this paper, it was clear that there were two modeling communities that were reviewing my paper, and they said it's known that the particle distribution at this distance is such and so forth. And I said, you know, I wrote back saying, how do you know this? You know, there are some observations, optical observations, which have constraints on particle sizes, but but you do not know, as a function of time and radial distance, what's the particle distribution unless it comes from a model. And so the two people were saying that it's known from their models, and their models gave different results. And this was my bottleneck.
That was my problem. We don't.
Okay, I mean, we see the bigness, and of course, if you don't believe in the theoretically well-founded expectations, then of course you just wait a few years, and then we have ALMA observations, and then you really have nothing to talk about. ALMA observations.
We observe the disk.
And we might even observe the vortices in the disk.
Yes,
Yeah. Absolutely.
This is the optical.
No, of course not. Optical.
Come on, I mean,
It's radio.
optical observation.
It's infrared.
I mean,
You simply can't observe it because it's of course hidden behind the dust. So you have to go into radio.
Yeah, then we will see some better signature of the dust, okay, but I'm talking about real. I mean, the question we was raising, I mean, exactly what the distribution of the, what is really essential to have an idea of the distribution of the Geraint size as a functional value. So this information will never be available. That is the point. Observational point of view.
No, that might be right. By the way, the same was of course true of the sun. It was clear by Eddington said, of course, you can never look into. Yeah, that's what Eddington said. You can never look into the sun, right? I mean, how can you possibly look into the sun? Never. And then you just waited. And then you just waited until 84, and then the rest Sasha can tell, right? So anyway, that was very exciting today, and we have now time for some a little bit more discussion about this afterwards, and then we have our program coffee at 3:30 o'clock. So thanks, John.
Thanks.